Hello, class, and welcome to Atomic Theories.
In this PowerPoint video, you are going to be able to explain how the atomic theory has evolved or changed over time. You will also discuss the contributions of Democritus, Aristotle, John Dalton, J.J. Thomson, Robert Millikan, Rutherford, Bohr, and the quantum mechanical model. The atomic theory began with Democritus, who was convinced that all material was made up of tiny particles that he called atomos, which means indivisible or uncuttable. Well, along comes Aristotle, and he simply declared that Democritus was wrong. Atoms don't exist, and everybody believed him.
Many years later, John Dalton came along. He based all of his research on three laws. The law of constant composition stated that the same kinds of atoms in the same ratios made up a compound. In other words, CO2 will always have one carbon and two oxygens. He knew about the law of conservation of mass, and he based all of his research on this law. He measured the reactants before, he measured the products after, and he found that the mass of the reactants always equaled the mass of the products. He also knew about the law of multiple proportions, the same elements but in different ratios. For example, carbon and oxygen could be CO or it could be CO2. Water, H2O, hydrogen peroxide, H2O2. He had 6 basic parts to his theory. All elements are made of atoms. Atoms are indivisible. All atoms of one element are identical. In other words, all oxygen atoms look exactly the same. But different elements have different atoms. Oxygen atoms don't look like fluorine atoms. He knew that all atoms are not created or destroyed, but simply transferred in reactions, and he supported that with his research, his experiments on the law of conservation of mass. And he also knew that elements can be rearranged in reactions, and they would combine to create compounds with whole number ratios. Now, I starred atoms are indivisible because we know atoms are divisible. There are things inside the atoms, such as protons, neutrons, and electrons. And he didn't know about isotopes. Turns out that not all atoms of one element are identical. For example, carbon has 3 isotopes, carbon 12, 13, and 14, and they all differ based on the number of neutrons. After John Dalton came J.J. Thomson. He furthered the atomic theory. He made the use of cathode rays. Radiation is produced when high voltage is applied to electrodes in a tube, and the rays would begin at the negative electrode and then travel to the positive electrode. But rays can't be seen, but they can be detected because they would make some materials give off light. Well, Thomson applied electric and magnetic fields to these cathode rays, and the rays reacted. He knew that the cathode rays were negative particles, and he discovered the electron. He was also able to calculate the electron's electrical charge to mass ratio. Many people refer to his model as the plum pudding model. I think a better description is the watermelon model. So picture a watermelon, and all of the pink flesh is positive. The positive charge is everywhere. And all those black seeds in the watermelon, those are electrons. So he pictured a positive sphere with scattered negative electrons throughout. Let's discuss a few other important advancements to the atomic theory. Robert Millikan used Thomson's charge to mass ratio and was able to measure the charge of an electron. Its charge is 1.602 times 10 to the negative 19th coulombs. He also found the mass of an electron, and as you can see, that is a very small number. Henry Becquerel, Marie and Pierre Curie, and Rutherford all did experiments with radiation, and this led to the discovery of 3 types of radiation: alpha, beta, and gamma. Let's take a look at Ernest Rutherford's experiment. He used alpha particles. Now these are the nuclei of helium atoms, so 2 protons and 2 neutrons. This means they're positive charged particles. He shot the alpha particles at a piece of thin sheet of gold foil. Surrounding that is a zinc sulfide coated screen, and whenever the alpha particles strike the screen, they produce flashes of light. He noticed where the flashes occurred, and he could determine if the atoms in the gold deflected the alpha particles. Well, here's what he thought would happen. Alpha particles are always positive, and they're very large, and they're very fast. He thought that they would slightly deflect if they hit an electron, because Thomson had said that the positive charge was spread throughout the atom, and he didn't figure these positives would affect the large alpha particles very much. Imagine a gigantic linebacker running down the field with the football, and a little tiny puny kicker's in his way. Don't think the kicker stands a chance. But what happened is that some of these alpha particles were deflected very large angles. In fact, some shot straight back at the source. This would be like firing a cannonball at a sheet of paper and it bounces back straight at you. So he concluded that there must be a densely packed positive force occupying a very small space. Based on his experimentation, Rutherford concluded that the atom is mostly empty space, that the electrons move in that empty space. But most of the mass and that positive charge must be in the center. He named this center the nucleus, and he knew that it was very small and very dense. He later discovered the protons in the nucleus. His colleague James Chadwick discovered the neutrons in the nucleus, which was no small task. Neutrons are neutral. It was really difficult to detect them. But what they could not answer was, where exactly are the electrons? Why don't they collide with the nucleus? I mean, electrons are negative, nucleus is positive. Don't opposites attract? And he could not explain chemical behavior. Now, there are more theories to the atomic theory, but I'm going to stop my discussion there. Instead, you are going to do some research. One of your discussion questions this week is going to be to research Bohr's contribution to the evolution of the atomic theory. You're also going to look at what the quantum mechanical model has to say about it. You need to explain both theories. You need to discuss the experimentation that led to the support of their theories. You need to cite your sources. You need to respond to at least 2 other posts. And you may need to research beyond the textbook. Keep in mind that not everything is in the textbook, and it's okay to go to other sources. Just cite them first.